Welcome back, Physical Science 20. This is the third section, heat capacity 6.3 in the heat unit, HT1. So here we're going to look at heat capacity. Starts off by saying oil, if you're heating up oil on the stove versus water, of course oil heats up a lot quicker than water. So we're taking a look at reasons why. Why does substance warm up or vice versa cool down at different rates? It has to do with the substance's specific heat capacity. The amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree C. That is referred to as the specific heat capacity of the substance. Sometimes it's defined in terms of 1 gram, but in this case we're doing it in terms of 1 kilogram. And if we look at this chart on the right hand side, we'll see specific heat capacities of various substances. And as we see here, water is a really high specific heat capacity. 4,180 joules of heat is required to raise the temperature of 1 kilogram of water by 1 degree C. And as we go down the list, we see it gets easier to raise the temperature of iron, copper, silver, lead. So it depends on the molecular makeup of the substance. Some are easy to get increase in that kinetic energy, whereas others are difficult. Okay? So different molecules require different amounts of energy to increase their kinetic energies by the same amount, and in this case, by 1 degree C. So of course we can do some measurements with this number, because since we likely won't be dealing with 1 kilogram and moving at 1 degree C all the time, we have to have a way of looking at how much thermal energy is involved when we have more than a kilogram and the temperature movement is more than 1 degree C. So that's where this equation comes into play. The total amount of thermal energy transferred from a warmer substance to a colder object is called quantity of heat. So we use a big Q or a little q to represent that. And if I take the specific heat capacity, which is symbolized as C, if I have more than 1 kilogram, I have an M there, and also a change in temperature. So the units will work out really nicely here, because C is in joules per kilogram degree C. I have so many kilograms for mass, so many degrees C for temperature. All the units will cancel out and leave me with joules for quantity of heat. Okay, so if we look here, and it may be worth pointing out that the change in temperature could be positive or negative. If the substance is absorbing heat, the final temperature, T2, will be larger than the initial temperature, T1, so it'll be a positive number. Or if the substance is releasing thermal energy, of course the final temperature will be lower than the initial. So if you take a small number minus a bigger number, you'll get a negative temperature. So so just be aware of that. The temperature could be positive or negative, depending upon the circumstance. So if you look at a question here, when 200 mils of water is heated from 15 degrees to 40 degrees C, how much thermal energy is absorbed by the water? So since we're absorbing thermal energy and we see the temperature is going up, we'll get a positive T value and also a positive Q value. Now one thing, water has a density of 1 gram per milliliter, so 200 mils is the same thing as 200 grams. But since our specific heat capacities are stated in terms of kilograms, we need to make sure our masses are in kilograms as well. And of course, 200 mils is 200 grams, and a change from grams to kilograms divided by 1,000. So 0.2000 kilograms. And my initial temperature is 15, final temperature is 40, so 40 minus 15, 25 degrees C. And then plugging that into the formula, MC delta T, mass times specific heat capacity of water, which is 4.18 times 10 to the 3 joules per kilogram degree C. And my temperature movement is 25 degrees. And you can see here the kilograms cancel, degrees C cancel, we're left with joules. So the water must have absorbed 2.09 times 10 to the 4 joules. Okay. Second question here, an empty copper pot is sitting on a burner. The pot has a mass of 1.2 kilograms and is at a temperature of 130 degrees C. The pot cools down to room temperature, which is around 21 degrees C. How much thermal energy does it release? So since we're cooling down, it's releasing thermal energy to the surroundings. So our initial temperature is 130. Our final temperature is 21, so 21 minus 130, negative 109. So yes, we get a negative number there. And then putting it into the formula, Q equals mc delta T, mass times specific heat capacity of copper. So just from here, 3.8 times 10 to the 2 joules per kilogram degree C. And there you see it, 3.8 times 10 to the 2. And then my temperature difference, negative 109. So kilograms and degrees C cancel, we're left with joules. And of course we get a negative value here for heat, which makes sense because thermal energy is being lost by the hot pot. It is releasing heat to the atmosphere or surroundings. Okay, another question here. Sample problem 3, a block of iron starts off at a temperature of 22 degrees C and heated up to 100 degrees C by placing it in boiling water. The quantity of thermal energy required to do this is 4.91 times 10 to the 5 joules. What is the mass of the block? Okay, so this is the case in which we know Q, we know C, we know T, rearrange for for M. So since it's M multiplied by C multiplied by T, divide by C delta T, divide by C delta T, and the formula becomes this. All right, so we have our thermal energy on top, specific heat capacity of iron. So just look back here, 4.5 times 10 to the 2 joules per kilogram degree C, and then 78 is my difference in temperature when I take 100 minus 22, so I get 14 kgs. All right, so 3 practice questions here. This will mark the first half of this assignment. When we're done the practice questions, I'm going to get you to go ahead and do questions 1 to 5 here, because they all involve that Q equals mc delta T formula, so to ensure that you're okay with that. All right, so maybe pause the video, come back, and we'll look at the 3 practice questions. So try them now, and then press play, and you can see how you made out. Okay, so if you had a chance to do these questions, key thing is setting all these up. Write down all your variables. So Q, C, M, and delta T. So if we look at our first question here, how much thermal energy, so question mark for Q, is required to raise the temperature of 2 kilograms of water by 10 degrees C. So we're told what the change in temperature is. We're raising it by 10 degrees. So we don't have a final temperature, we don't have initial temperature, we're just told the difference is 10. Mass is 2.0 kilograms. It's water, so the specific heat of water, of course, is 4.18 times 10 to the 3 joules per kilogram degree C. So it's just a matter of putting it into the formula. I just have mine as C M delta T. Yours could be M C delta T. It doesn't really matter. Also, you may have used a capital Q. I used a small q. Doesn't matter. So substituting the numbers in, my specific heat times mass times change in temperature. Of course, kilograms cancel, degrees C cancel. I'm left with 8.360 times 10 to the 4 joules. If I look at sig figs here, don't use this number, it's pulled from the chart. Use the other ones in the question. 2 sig figs, 3, so 2 sig figs. This is a 6, so that gets bumped up to 8.4 times 10 to the 4 joules. Okay, number 2. A glass window has a mass of 20.0 kilograms, is heated to a temperature of 32 by the sun. How much thermal energy is released by the window to the surroundings if it cools down to 5 degrees at night? So we have an initial temperature, a final temperature, a mass. We're told it's glass. So looking back here, glass is 8.4 times 10 to the 2 joules per kilogram degree C. So there we have it. It's 8.4 times 10 to the 2 joules per kilogram degree C. The mass was 20. The temperature, it was initially at 32. It ended off at 5, so that makes a difference of minus 27, which is okay because we're releasing thermal energy, so our temperature is expected to go down. So Q equals Cm delta T, specific heat capacity, times my mass, times my degree C, and again kilograms and degrees C cancel. I'm left with negative 4.536 times 10 to the 5 joules. we have 2 sig figs here with 5.0, so I round it off to 2. And of course, the negative implies that heat or thermal energy is being lost. So I should get a negative number, and in fact I do. Okay? The last question, I think it has a bit of a twist to it. An aluminum block absorbs 1,000 joules of energy from the sun when its temperature increases by 5. What's the mass of the block? So we're told the change in temperature is 5. We are told the thermal energy, it is aluminum, so I'm going to have to go back, look at what aluminum is. 9.2 times 10 to the 2. Okay, so 9.2 times 10 to the 2. Okay, I'll just delete that. And we have thermal energy, or change in temperature is 5. So we're looking for mass this time, so divided by C delta T, divided by C delta T, I get that. So I have my thermal energy on top, C on the bottom, T on the bottom, joules cancel, degrees C cancel, kilogram will get flipped up to the top. So you can see that we end up with 2.173,913 kilograms, and of course 2 sig figs. So we keep the 2, we keep the 1, but this is the 7. So 2.2 kilograms is our answer. Okay? So that's it. Those are the practice questions. So at the end of this part 1 of this segment, do questions 1 to 5. Those will be handed in, and then in part 2 of the video we'll look at the second half, and we'll be able to do the rest of the questions. Okay, see you again.